All right, so today we are discussing world models. So I'll just jump into it. Uh, so basically, the main idea behind world models, at least from my understanding of the paper, was that they wanted to convert the traditional approach of environmental interaction, plan, and execution to a more supervised learning approach, where you can, rather than interacting with the environment and training the model, you can more or less model the environment itself. Uh, so there is some correlation uh, with large language models as well here, where large language models have some sort of, they try to model the language. So you have a modeling of English, a modeling of grammar, vocabulary, so on and so forth. Uh, but in this case, we are trying to model the environment since we are dealing with the environment directly. Uh, so this is more or less the whole world model, very summarized view. But there are three parts to it. So there is an autoencoder involved. There is a MDN RNN involved, basically something which adds a temporal dimension to predict. And then there's a controller which basically predicts what sort of actions you have to take. So I'll just show you, dive into it one by one. Uh, so the vision model basically tries to convert your observations or images from the environment into a low dimensional hidden state. And the memory basically tries to understand what from this incoming Z, uh, what would be the next hidden states and what sort of actions are going to be performed. Uh, and so basically it tries to learn the different dynamics in the environment. Uh, and I also can predict what sort of future states the model will see. Uh, the controller basically tries to predict what sort of actions will be involved next. So we have three. The world model is basically a part of all these three models. I mean, it is sequential sort of an inference here. So before I go into word models, do you guys know what autoencoders are? So I thought I'll just give a small no-brainer on autoencoders.
Can you explain it briefly? Actually, I don't know.
Yeah, sure. So so an autoencoder is basically is like what we're trying to do is we are trying to learn a compression of an image. So we have an input of Mona Lisa here. So this should be a clean image, by the way. But it can also be a noisy image. So you can have something like um, so you could basically have one thing. One thing is that you learn a compression. So you can use this compression in different ways. One could be that, for example, during streaming, you could use it to reduce the usage of data. So you could compress your input image into a smaller size, and you could stream it down, and you could have a small decoder network on your mobile phone that restores the original image from this small compression. Another way autoencoders are used is they basically can also be used as noise removers. So you can have a noisy image as an input, and you can have as an output a clean image, and your decoder learns to remove the noise from the input. So that is another way to learn these. I think apart from these two, another way could be something like neural in painting. So you could have, maybe you could remove like I know on Hugging Face there are those, those uh, uh, is it white mark? Yes. watermark. Sorry, yeah. So these watermark removers, you could basically just uh, you could, so for example, if you have like a, this is one way to do it. So you could have like, if you
Um,
have this small watermark, you could train autoencoder to remove that as well. That
okay,
is,
so this is supervised only, right? Or
sorry.
this is supervised or
It is
It
self-supervised.
is supervised. It is
no.
yeah,
Okay,
self-supervised.
okay. Very good.
So you're basically from the input, you're reconstructing the same input from the input. So you're
Yep,
taking the input, and from the compression, you're reconstructing the input. So your loss function is like a reconstruction error, uh, is the loss.
got it.
So what our end model uses is not really an autoencoder, but a variational autoencoder. So variational autoencoder just changes the latent vector to something different. So instead of just having a compressed vector representation of the input, it basically tries to predict a Gaussian. So it predicts the Gaussian. It assumes that your data distribution of baby images here is a Gaussian, and it basically predicts the mean and the standard deviation of the Gaussian distribution. And the decoder uses samples. So this is a bit of a stochastic approach, where you can basically change this Z, and you can have different outputs on the decoder. I'll show you also in the how they do it on the world model. Uh, but here in this specific one, we don't use the we don't change the Z so much, because we have something, a stochastic aspect even in the MDN RNN that allows you to tune the stochasticity a little bit. But I think the main reason they do that is because your latent vector is quite smooth. So you don't have holes in your latent vector compared to something that an autoencoder compression has. So I can show you. That's the one. So basically, this is the variational autoencoder, and so you can basically change the Z, and you can see how the decoder changes. So the stochastic part allows you to change the different. I mean, you can play around with the sampling from the distribution, uh, and you can see how the reconstruction changes. So this way, so this is one part of it. This is the vision part, and then we have. I think I'm out of stuff. So then we have the MDN RNN model. So what the MDN RNN model does is it basically takes the input from the vision model, this input, and it basically takes the action, it takes the hidden state, and it tries to predict what is the next latent vector. Uh, so, so so basically, it tries to model what the latent state vector will be at the next state given an action, a current compression, and what it has seen over its memory at the time t. So this RNN gives you a Z t plus one, and then you have something called an MDN with this temperature parameter that allows you to control what the output will be. So I won't really dive in much into what this mixture density network does, but they have something here where you can control the different. So you can have a pen stroke, and you can see what it's predicting that what the image will be, and they adjust this. They play around with this temperature a little bit to train the next part of the world model. Uh, and into the control model. What the controller does is it takes the Z from the VAE and the learned memory of the different states it has seen from the MD and RNN, and basically predicts what the next action is. So uh, so putting everything together, you get this nice flow diagram. So you can basically so you have this image observation, and you get this compression out, and so this compression can go into the goes into the MD and RNN. So first you train the variational autoencoder. Then once this is trained, you freeze this, and then you train the MD and RNN. And then once these both are trained, you freeze both of them, and you train the controller. This is how more or less the flow goes. But I'll go into the training dynamics into more detail in the next step. Uh, so what you could do is you could have, so you have the encoder part of the variational autoencoder, you have the decoder part, and your observation goes in, and you have latent vectors coming out from the VAE. And this latent vector, you feed it into the MD and RNN, which gives you the long-term memory of what it has seen over all the different during its training. And the same Z goes into the controller, and this predicts the action. So now what you could do is you have two ways to do it. You can basically have some form of self-supervision here, and you can take this action and put it into the MD and RNN to keep generating the next hidden state and learn the model that way. Or you can obviously you can put it into the environment, get the observation, or maybe even take it from the decoder and take it from the decoder and do it again. So these are more or less two ways. Uh,
Yeah, much more like seems like MDP to me.
yep. So it's pretty similar, but I mean it is a MDP formulation, but in a standard MTP, the main part is that uh, you are uh, you are always in an interaction with the gym environment. But in this case, your MDN RNN basically is able to model this environment directly, and you just have a single observation in, and you can basically have a varied autoregressive inference of, I think, yeah, you can have an autoregressive inference of what sort of state you'll see in the future, what sort of state it has learned in its memory per se, and then you can obviously the controller is the action. So so this is basically how they are formulating their rollout. So they have they're getting the V encoder embedding the latent state, and also I think they have not put where they got the edge from. But anyhow, they're getting the edge from the RNN forward, or this is the existing state, the initial state, and then they get the action, and it goes on this way. We also have yeah. So basically, the training procedure is like that. They start with some form of some random policy. They train the first stage is always to train the variational autoencoder to encode your hidden state. In this case, hidden state of 32 dimensions. Then you train your MDN network to model what the next latent vector would be. And so once these two are trained, you freeze it and you define your controller. And the controller is trained on something called CMAES. I really didn't get much of it, but it was basically trying to it's trained on rewards. But here we have some form of supervision based on one. But here we are basically calculating the cumulative reward and training to maximize that reward, training the controller to maximize that reward. Uh, this is more or less how it is. And so what they did was they were able to the main conclusion was that they were able to train the model using this MD and RNN, and it was able to do pretty good. So they had some. So their agent was able to achieve a score of 906 for the world model compared to compared to using something like a DQN uh, over I think over 100 trials. Uh, so it went pretty good. Uh, so something, and then they also did the same for the Doom game, uh, where they had the same approach again. Uh, Obviously, I think higher parameter count was the same. Yeah, higher parameter count, and I think it also managed to achieve pretty good results. So it achieved uh, 1100 time steps beyond the 750 in a more virtual environment. So this was more or less the conclusion of it. And there's a lot more into what goes. I mean, a lot more granularity into what things exist in terms of the biases and the sort of architectural aspects. And this is a overview into how they basically did it. Uh, Something similar to this would be something like, where is it? Just use, would be something like what World Labs is doing. So what they do is they have a input image, and using the input image, they are basically modeling the 3D world from a single image. So this was something I was exploring for the video game design course, but didn't really get time. You can also,
Um,
yep,
so, do you remember? I think it was Google. I don't know which company it was. From the text input, it would generate 3D inputs. Is that also based on this, or?
it is. I think it is. I'm not sure which model it is. I think I remember
Yeah,
the name.
I think at that time it was pretty much hyped
Dreamer
up.
V3 is
So,
your, I think you're what you're talking about. Yeah. But
V3.
that's not based on text input though.
oh, is it okay?
Yeah.
But the end
But
result is pretty
it's
much that. Uh,
like it's very similar to the basically it's a world model approach. Yeah.
Okay.
you can basically scroll around the different worlds. Uh, the museum as well.
So one thing that we need to note around the world model approach is that like basically in RL, whenever you train, right? So if you're training on a unstructured input, uh, for example, in this case an image, then in that case you would like to encode your data really well. But if you use an autoencoder approach, right, or with just the encoder itself, then in that
Hmm.
case you cannot account for a very simple thing, that what happens when your environment has different kind of noise inside, right? So I mean right now you're in your simulation environment, you might have worked with two cars, but what happens when suddenly a different car comes into the picture, right?
Right.
When you do variational encoding, at that point you can actually account for those things. It's assuming that okay, if my data set has
Hmm.
like maybe even 5% of times where it has three cars, it should be able to at least have it in the learned distribution as well, which is not true for an autoencoder, because for an autoencoder, because it has only come for 5% of times, it will probably even not have the weights updated properly to actually account for it, because an autoencoder is effectively a hash map,
Right.
and a hash map cannot account for it. So that's one factor. That's also the reason that why it can probably translate better into unseen situation of the same environments. Then the other aspect of it is the self replay. And that's what also the paper at the very beginning also shows, that the man is cycling and he's thinking about cycling. That
Right.
because you have a RNN model which kind of outputs the next state, and you can again take this state and then put it in the same model again and again. So you can basically do a training where you no more have to interact with the environment. And that
Right.
kind of unlocks
Yeah,
this whole
that's
idea that
Dyna in RL, right? It's similar to
ha
Dyna.
yes, ha yes, yes. So basically you're learning the model as well, and as
Yeah,
well as the policy.
yeah. But you said the model that you showed here, it would account for the 5% chance that other car would come in the vicinity of the your subject car. So you said it would handle or it would not.
It will handle. So right now, because it's a variational
But
setup, it will matlab, as in like because you're learning a distribution, so within that distribution it should be there. It's not that the
okay, so
autoencoder will not. It's not.
With the, with
oh,
the
okay,
with the
okay.
autoencoder, you're basically limited by the latent, but here at least you are modeling more a distribution. So you can literally sample different parts of the distribution and look vary that. Uh, but here, I think in this paper, they don't. I don't see anywhere they varying the z so much. Uh, it's more the MD and RNN that's predicting.
Wait, the self replay will have that, right?
Right.
I mean, it's
Perhaps.
not that
Perhaps.
they don't have to vary the z, because they are not exactly outputting the image, right? They don't need to use the decoder that much. Decoder is only for reinforcing, like not reinforcing actually, just as a kind of a secondary loss to make sure that we
Right.
encode the image really well. So
Right.
since we're not doing that, but because there is a decoder, your you know the latents are good enough. So whatever the MDRNN is outputting as a z at any point in time. So in your left-sided image, that z t plus 2 or t plus 1, they are in self good enough latents. So if you like put it into the decoder, you're going to get legit game world states.
Yeah, that's true. Because it's already trained, right? It's a
Yes,
frozen
yes, yeah, exactly.
frozen wheel. Right. I think the second part I was looking at, I was seeing how I could draw some correlations with the latest state of the art. So it seems like the modeling bias, the inductive bias of modeling is pretty similar. Uh, it's still a hidden state and some form of concatenation and prediction and further loss. Looks to be pretty similar in that sense, but I still haven't read this paper in detail. Uh, if you guys have, feel free to take it. But I was just looking at this image and drawing correlations with the one in the PowerPoint.
Wait, VJPA is the more recent one, right? Okay,
Yeah.
yeah, this one came up recently. Yeah. Yeah, I haven't got to this paper. I was just covered up. I was looking at IJPA.
So, but it seems pretty similar. It's just the
It is.
same
I
approach.
mean, the only thing that like actually
Maybe
struck me very
they.
differently
Mhm.
is how you do inference. Basically, that longer time step inference based on gradient descent is what like struck me as a little bit different. I was like that I found very interesting.
Right. I hope I could explain word models. So, any questions? Uh, I didn't have many slides, as you
You made slides. That's more important.
can
Yeah.
So I've been following pretty much what these guys have been doing, which got me pretty interested uh, into world models in the first place. Uh, and if you see the team, yeah, it's the same people we use for DL, right? So So we have Justin Johnson from the DL lectures. If you guys have taken DL, not sure. So, I guess no questions then.
No, as of now, I don't have any questions actually.